guys are flying.
I want like better flight time, well, whatever.
I'm gonna break my iPad here. Seems pretty good.
And last time was really good. I was like, alright, I'm done. I was like, no, you can. So I was like, you was coming down. Filled it up for her.
How's that?
He's okay. I think he's better today.
Really?
Yeah.
Really? Okay.
No, yeah, seriously. I like texted him this morning and he was like, yeah, I like don't feel like I'm burning up.
That's
Yeah.
huge.
Yeah.
That's huge.
So, I don't know. We're just still crossing our fingers.
Yeah, no, definitely, definitely. Yeah, this is not out of the woods. But, you know, this virus just takes so long to fix it.
Yeah, especially like someone of his age and like he's literally like the high risk person.
Oh gosh.
So like yeah, it's just you know.
That's okay. Okay. He's young. He's young. Whatever age he is, he's young. That's, yeah, I always thought like 60. When I was a kid, man, I was like 60. You've had a good life. You've lived 60. You've made it. You know. And I'm like now I'm 59, and I'm like 60's pretty young. 60's pretty young. I still have one person who still has to take the quest. They had COVID, and so they were out for 3 weeks. They were out. Well, they've been doing virtual, but I just can't make somebody take a quest if they have COVID. This is against everything in me to. Oh, I can't wait till I can teach you guys without a mask. I can have you guys without masks. It'll be, and I'm believing next fall. I'm believing next fall. I get a sense we'll be masked up in January, but maybe even by April, or March, we may be able to, after spring break, we'll be without masks. Okay, we are going to have a quest. We are going to have a quest next Friday. We're going to have a quest next Friday. So write that down. Write that down. You will definitely get your quest back, whatever that means, virtually, on Monday. They're graded. They're graded. I just can't release them. The average I think was like 76, something like that. I think was kind of the average. Which is good. Typically my averages are in the 60s, so. 13.1 and 13.2. 13.1 and 13.2. That's the content. That's the content that will be on the quest. There's no what on the quest. Proofs, okay? Which will make the quest a little shorter. So I can't extend that much class time. It'll be a lot easier because I'm just handing it out and getting it back. Okay, I guess let's stand up, not breathe on everybody. It looks like we're pretty good distances. I don't think I'm going to annoy anybody up here. Stretch. Yeah, I don't think I can annoy anyone. Okay, sit back down. Okay, write down this. Imagine that I've got a space curve, R of t. R of t. And I know this about my space curve. The norm of R of t, the norm of R of t is always the same number. It's a constant. The norm of R of t, let's just say, is 5. The norm of R of t is 5. And let's give ourselves a domain. Let's say t is going between a and b. Let's say t is going between a and b. So we're in this scenario. We've got a space curve as t goes between a and b. We've got a space curve as t goes between a and b. And the norm of every one of those position vectors is 5. So draw yourself an xyz. Give yourself an xyz, an origin. And try to visualize what this space curve might look like if the norm of every single vector, every single position vector is 5. Try to visualize what this might have to look like. So again, web assign is due tonight at 11:59. They'll always be due at 11:59 on Friday or any day, now that I can change that. Quest next. Friday, 13:1 and 13:2. 13:1 and 13:2. So try to visualize what this space curve looks like if the norm is always equal to 5. Can you guys hear me okay in the back? Bridget, can you hear me? Yeah. Zach, how about you? Can you hear me? Okay, so let's imagine that I've got something, okay. I'm gonna start at a point A, maybe. So here I am. Here's my this is my R of A, pointing to there. Okay, and what do I know about the length of this vector? What do I know about the length of this vector? It's 5. I know I'm going to end at some point, maybe over here. I know I'm going to end at some point, maybe over here. Here's my vector R of B, but its length is also 5. And for any t I pick in between A and B, I'm going to draw a space curve. But if I just pick a point on the curve, and the t value I pick from my domain, I'm going to have a position vector. Let's just call it R of t. And what's the length? What's the length of that R of t? 5. Now, can you guys visualize what this looks like in three-dimensional space, where we fixed the length of our space curve? We fixed those. Could you do this? Could you come up with a space curve whose length was always 5? I'm like, well, I don't know, Dr. Warren. Give me a space curve. Give me a space curve. I'm like, Dr. Warren, what are you talking about? You should know, okay? A space curve. A vector value function is the definition of a vector value function is a order triple of 3 real valued functions. So give me 3 real valued functions.
Secant of t.
Ooh, secant of t. Good, Michael.
T squared.
T squared. Natural log of t. A beastly space curve. Give me a domain. Give me a domain for this where it would be well defined. You know, like Michael's like, damn it, I picked secant. What is secant again? Secant is 1 over cosine. Doesn't that piss you off? Didn't you really want it to be 1 over sine and cosecant? You're like, damn it, can't you keep the S's and the C's, right? It's because you don't really know what secant means. You don't really know why it's called secant and why it's called cosecant. And I shouldn't go off on this tangent, but I just have to do it just because. Guys, because people don't understand, when they learn about trigonometry, I don't know how it happens in the US. They get one triangle, but they don't draw the most important triangles. So let me make sure you guys have this as you move along. If I think about this, I've got my Cartesian system, and I've got theta. I've got theta here. Let's just make it 1, the unit circle, I drop this. I drop this. This distance would be, that distance from there to there would be sine theta, we got that. This distance would be cosine theta. What they never draw is this triangle. If I come off of here with the tangent line, I mean, which is just like vital to the Greeks, this is a right angle. This is a right angle. This distance from here to here is tangent of theta. That distance from there to there is tangent of theta. That's why it's called tangent. This distance, this hypotenuse, is secant of theta. It's part of a secant line. This is part of a tangent line. If I go up here, this is the cotangent. And can you guess what that distance is? Can you guess what that distance is? The cosecant of theta. There's a triangle that saves kids. There's a triangle that saves kids. Because it makes sense. As I move my angle, if I move my angle up to pi over 2, what happens to the length of tangent? As you move your angle up to pi over 2, what happens to that length of tangent? It gets infinitely large. The same thing with the secant. It's just even bigger. It's the hypotenuse of this right triangle. So it just swings up, and you can see that this, as we move up, the cosecant's going to go to 1. It's like, if I think it means the cosecant's going to go to 1, the cotangent's going to go to 0. This triangle in the US is not taught in most high schools. It's just not taught. It's just, okay. So let's look at this triangle and think about Michael's function, which is there, okay. When would secant be bad? Where would secant be bad? What angle might make secant bad? We don't want infinity. Any of the pi over 2s. Any of the pi over 2s, okay? If you swing it around, it's going to make it bad. So let's just say we're going to go in between 0 and pi over 4. Or maybe even more fun, between minus pi over 4. Oh, crap, we got natural log. Let's go between pi over 16 and pi over 4. So there's the domain of the function. There's the domain of my space curve. Now, could you turn this into a unit vector? Could you turn this into a unit vector? Could you turn this into a unit vector? How do you turn a vector into a unit vector? Flashcard, you'll see that one if we took that quest. Flashcard, how do we turn a vector into a unit vector? Divided by its norm. So let's do that. Let's take this and divide it by its norm. Let's take this and divide it by its norm. This is going to be a new function. This is going to be a new function. Maybe I'll call it Blackman even better, f of t. Now, what would the norm be? What would the norm of that vector value function be? What would the norm of that vector value function be? Square root of secant squared plus t to the 4th, then plus natural log of t squared. Does that make sense? Does that make sense? Do you guys want to plot that? I mean, I'm just saying. Do you guys want to plot that on its domain? Do you want to plot that curve? Do you want to plot that curve? And you're like, Dr. Warren, is that a yes or no? Is that a yes or no? Do you want to plot that beast? Okay, what's the multiplication between this square root and this vector? What's the multiplication between this square root and this vector? What is the multiplication between this square root and this vector? I mean, think about it, count 3. How many multiplications do we have? We have our cross, we've got our dot, and we have our scalar. What is this, a dot, is this a cross, or is this a scalar? Is this a dot, is this a cross, or is this a scalar? It's a scalar. So we would move this square root into each of those components. We would move, but we know the norm of f of t. The norm of f of t, by the way we force this, has to always be 1. The norm of f of t always has to be 1. If I wanted to make it 5, I would just multiply everything by, if I want to make it 5, I just multiply everything by 5. So you can always do this to a function. You can always do this to a function. But visually, when you have a space curve, and the length is always a constant, what does that space curve look like in three-dimensional space? It's a circle, but we're in 3 dimensions.
It's a sphere.
It's a sphere. It's a space curve that's lying on a sphere. Do you think those kind of curves are important? What do we live on? Well, not really, but what do we kind of live on? A sphere. What's the moon? Sphere, okay? Are there spheres a lot? Are there spheres a lot? I mean, like we will. So spheres are important, and so what we've got here is we've got a ball. We've got a ball of radius 5, and I've got my space curve that lies on. I got my space curve that lies on that sphere. Okay. Could somebody find the tangent line? Could somebody find the tangent line to this point on my space curve? Could somebody find the tangent line to this point on my space curve? When I say line, you say, when I say line, you say, when I say line, you say a plus TD. I need a position vector and I need a direction vector. I need a vector that points to the line. And then I need a vector that, what's the D stand for, guys? What's the D stand for? A plus TD. What's the D stand for? Direction. It directs the vector. I need a vector that lies on the line, and I want it to be perpendicular to my curve. But now my curve's sitting on a ball. Well, we found out yesterday that the derivative sits perpendicular to the curve. The derivative sits perpendicular to the curve. So what would the equation of the tangent line be? What would the equation of the tangent line be? It would be tangent line. This is a flashcard. Tangent line to a space curve. Tangent line at the point C. T equals C would be R of C, which is my position vector, which positions my line, plus T times
R prime of C.
Very good, right? R prime of C, which does what for the line? Which does what for the line?
Directs it.
Directs the line. Which directs the line? So let's go back to Michael's original. Let's go back to Michael. This is not going to be, we're not doing this. Okay. We're not going to do this. But let's imagine that I picked like pi over 3. T is equal to pi over 3. Find the equation of the tangent line to Michael's curve. To Michael's curve at the point pi over 3. We can't even plot it. We don't even know what it looks like. We know it's complicated. Find the equation of the tangent line. Okay, sadly for sake of time, what's the flashcard you want to memorize? Don't look at the board. What was the flashcard you want to have memorized by next week? What's something by next Friday? What do you want to have? I say tangent line, you say ROC times tangent lines. Now, how many people can find the C? How many people think they own the C? What's the C? 5/3. The C would be pi over 3. The C would be pi over 3. So just plug that in. So this is the tangent line. So I'd have r of pi over 3 plus t, there's my parameter, r prime of pi over 3. Now r of pi over 3, good luck. Michael gave us a fun curve. I'm just going to write it as secant of pi over 3, pi squared over 9, and the natural log of pi over 3. T is what creates the line. T is what creates the line. Now what's r prime of t? What's r prime of t? Now this is where, how many people like the middle component? How many people got the middle component? How many people think they can give me the middle component? What's that? 2t. How many people remember the derivative of natural log? What's that? 1 over t. Now I had some of you guys in 235. What's the derivative of secant? Secant tangent. And so if I was thinking about what my direction vector would be, it would be secant of pi over 3 tangent of pi over secant tangent pi over 3, 2 pi over 3, and 1 over pi over 3. And so this would be the equation of my line. That would be the equation of my line. And that line would sit what to the curve? That line would sit what to the curve at that point? Tangent. It would sit tangent. Again, do you think tangent vectors are important in applications? Do you think tangent vectors are important? Tangent lines are important in applications? Now, if we had time, guys, what I would do right now is I would just hop on that graphing program and I would just plot this. I would just plot this. And then I would plot this line. And then you guys would see that curve, which would look incredibly complicated, because I'd have to find the box so you could actually see all of it. And then you would be in awe when you actually saw that line sat tangent to that curve. You'd be like, wow, that's incredible. So just say that. Let's pretend we did that. Just say that. Well, let's just say we did. Let's just say we did. Just say, wow, that's incredible. Dr. Warren, I didn't believe you. I didn't believe you. But now I've just seen it with my own eyes. I've seen Michael's curve plotted in this program. I've seen the line. I see the position vector, pi over 3, and it lies freaking tangent to the curve. Now in general, if you've got a curve, here's my position vector, maybe there's my tangent line. Does this look perpendicular? Does the position vector look perpendicular to the direction vector? Guys, if that looks like 90 degrees, you've probably been drinking, okay? How many people realize that in general, the position vector and its derivative aren't going to be at 90 degrees, Draw a circle. Let's go back to 2 dimensions. Draw a circle. When you draw a circle, you need what from geometry? You draw a circle, you need a radius and you need a, what's the other important thing if you're going to draw a circle? A center. So give yourself a center. Now pick a point on your circle. Okay, now draw the radii from the center to that point. Now draw the tangent line that runs through that point. what do you notice about that radius and that tangent line? What do you notice about that radius and that tangent line? They're perpendicular. And it will also be true if we're drawing on a sphere where the position vector is at the origin and the center is at the origin, that this vector will also sit tangent to my position vector. Well, in general, it's not true. I erased it over here. And if it's in the fact that, in fact, the norm of the vector, if the norm of the vector is equal to a constant, then you're drawing on a sphere, and then the derivative vector will sit tangent to that position vector. But math is the most important thing about math. Math is proof. How could we prove that? That if you have a space curve that's always equal, this norm is always equal to a constant, it's being drawn on a sphere, that the position vector pointing to the tangent line and the direction vector of the tangent line, the derivative vector, always must sit perpendicular to each other. In this rare case, R of t will be perpendicular to R prime of t. This is hard, right? I mean, think about it. This is hard because with a circle, we got all what the Greeks gave us. But sitting here on a sphere, this is a much more complicated problem. The proof is very, very elegant as far as what the Greeks gave. But watch this proof. This is really, really sweet. Well, the norm of R of t squared would be equal to what? If the norm of R of t is 5, the norm of R of t squared would be equal to what? 25. And this is for all t. Well, then the derivative with respect to t of the norm of R of t squared would be equal to the derivative with respect to t of 25. But what's the derivative? What is the derivative of 25? What is the derivative of 25? 0. Okay, quest 2. What's an identity that's equal to the norm of a squared? What's an identity that's equal to the norm of a squared? It's vital here. What else is equal to the norm of a squared? Cosmo, you got anything? Cameron? Michael? No, probably Lagrange identity. We used the Lagrange identity. Red.
It's like the norm of the product of the norm of two vectors times like the cosine of the angle between them.
I like that. The cosine is a good pen. Zach. Mason. Bridget. Raylan. Robert. Emily. Let's see if this. Rachel. There you go, Rachel. There we go. Cheat off Rachel on the test. No, just kidding. Just cheat off Noah. Like I said, my daughter who's a senior, I asked her, like, sweetie, so like, how many students do you think cheat on online evaluations? And she just started laughing. And that's when I know, no, we're done with online. We're done with online. I'm bringing my students back into old-fashioned classroom, It's just too tempting. It's just too tempting, especially when you're like, everybody else is doing it. Everybody else is doing it. And as she was a child, I'd be like, did you do it just because everybody else was doing it? Which is my mother. I'd hear my mother saying that. Why did you push his head into the mud? Well, everybody else was doing it. So. He's your brother. You shouldn't do that to him. Okay. Rachel said, what's equal, let's see if you remember now what Rachel said. What's equal to the norm of r of t squared? R dot r. So then the derivative of r of t dot r of t in this scenario, when we're drawing on a sphere, would be 0. Do we have a product rule for dot product? Do we have a product rule for dot product? What is the derivative of r dot r? What is the derivative of r dot r? It would be r prime of t dotted with r of t, that crazy plus in our product rule, plus r of t dotted with r prime of t is equal to 0. How many people are following so far? How many people are following so far? Okay. Is the cross product commutative? Is the cross product commutative, Raylan? No. It's anti-commutative. Is the dot product commutative? Yeah. Is the dot product commutative? So would r prime dot r be the same thing as r dot r prime, just using that commutativity? And so if I just switched this one and made it r prime dot r, just made it r prime dot r, how many r prime dot r's would I have? How many r primes dot r's would I have? 2. So this would imply 2 r prime dot r is equal to 0. This is a real number. This is a real number. When you have 2 real numbers multiplied together that equals 0, what did I just say? The algebra says one of them has to be, at least one of them has to be 0. How certain are we 2 is probably not 0? How certain are we 2 is probably not 0? So the only thing left then is that r prime dot r is equal to 0. Which tells me what about those 2 vectors? They're perpendicular. This proof saves you about 3 pages of geometry. This proof saves you about 3 pages of geometry to try to make the same argument. And that's a really important identity. It's going to come back over and over again in this class. Okay, but guys, in general, holy heck. You got a little JMU, look at this crap. Sorry, I could have died for you. For you guys. No, I don't think I would have died. I don't think I would have got hurt that bad. I mean, if Cameron can write that thing. You got that there?
Yeah, I have a question about that. Would that imply that the derivative would be 0 because the vector itself could say you could take the derivative of 0?
It doesn't imply the derivative is going to be 0. It implies that the derivative vector will sit perpendicular to that position vector.
Yeah, but if you're like doing the dot product equals 0, one of them has to be 0, wouldn't it have to be 0?
Oh, I see what you're saying. That, say that again.
You can have both of them be 0 and it would be 0, but it couldn't be just the vector because then the derivative would not be 0.
That idea that if you have 2 real numbers, and their product is 0, then one of these has to be 0. With this product, that real number property doesn't follow. So you got to be really careful. But you've already learned, like, it's tempting to say, oh, but you know that's complete crap. So you can't extend as much as you. And where was I? Let me go back here. Okay, thanks for other people were probably asking the same thing. I'm up here for a reason. What was I up here for? Oh, in general, guys, for most space curves, that's not true. What's forcing that? That we're drawing our space curve on a sphere, or we're drawing our space curve on a sphere. stand up, stand up, stand up. Look at your watch, clock, everything that's going on. Then tell me what time it is. What? 10:16. Okay, don't look at your notes. I say tangent line, you say. Okay, good. R prime of C. R prime of C. Okay, sit back down. So I'll have, okay. Are you guys sure you can hear me through this? Are you sure you can hear me through this? Guys, I just want to hit this. Like if I had Michael's function again, and suppose on the quest I said, well, give me the equation of the tangent, give me the equation of the tangent line at the point pi over 3. I say that, and you guys wrote down, oh, it's yeah, you do that, and I'll have students do this because they're panicked, they're taking a timed evaluation, I get it. But then I'll ask them, you know, like, you guys remember when we were talking about lines in chapter 12? Does that look like the equation of a line to you back in chapter 12? Does that look anything like A, like for example, 1, 2, 1 plus t times 3, 4, 5. Does this look any more complicated? Does it look slightly a little more complicated than that? Does that look more complicated than that? This ain't a, that ain't a line. That ain't a line. That is a wild function. That is a wild function. You've got to plug in the C. The moment you put a C in, number, okay. Number. If you forget it, do I have to punish you? If you forget it, do I have to punish you? Yes, because imagine you sent your astronaut who's expecting to go on a line on that path. Might he be freaking pissed at you? He's expecting this. I'm just going to take it back, take it easy. I got the right stuff. And then you send him on that flight. Okay, just saying. Okay, let's go back to Math 235. Let's see what you remember. Gentlemen, I taught you. And Ellen. And Mason. Okay. Cosmo, I don't think I had you in 235. From 235, what's our definition of this? What's the definition of that? What is that called? The what? What's this called? The integral, the definite integral, say that. From A to B. What's the definition of that? Calculus is about limits, derivatives, and integrals. We've been talking a little bit about derivatives. Now let's bring in an integral. I know I shouldn't be back here. Okay, just share what you have with somebody else. Just share. You don't breathe on them. Don't get close to them. Show somebody else what you have. You'll feel a lot better. You'll feel a lot better when you show them what they have. Okay, how many people had nothing, literally nothing in their gray matter for the definition of the definite integral? Math is proof, or yeah. No, math is proof. Calculus is about limits, derivatives, and integrals, one of the big three. And we've got nothing in our gray matter for the definite integral. So let me remind you. Guess what? The morning class didn't, not one person had anything either. Okay. Every other time I've taught Calc 3, nobody's ever had anything. When somebody has something, I'm just going to retire at that moment. They're done with me. Okay, they're done with me. So, but you guys still need me. Just like everything else in calculus, it's defined in terms of a limit. It's defined in terms of a limit. In this case, it's a little bit different than the limit as x approaches c or t approaches c. It's a limit going to infinity. It has a different definition, but it works the same. And then it's defined in terms of the summation. The moment you see that symbol, you panic, because it's Greek. It's a Greek sigma. Anything that's Greek in any science, math, or engineering class, you immediately panic. You'll never understand it. Theta. Oh gosh, not a theta. Epsilon, delta. No. Because it's a summation, it's got to have a starting point and end point. Now, let's see if you guys remember anything else now that I've got that started in your brain. What are we adding up? What are we adding up, guys? The function, I mean, we're taking the integral of a function. The function has a domain and a range. True or false? Is that in our definition of a function, domain and range? What are we plugging into our function? What are we plugging into our function? X, yes, we're going to plug in X. They're X sub K's. They're X sub K's. So we're plugging specific points in. We're plugging specific points in from the domain. What else is there? What else is there? We're not just adding up function points. What else is there? The delta x. Do you remember the delta x? Now, right now, this is a bogus definition. Sorry, bogus is not a word you know. That's the 70s. That's my 1970s lingo. That's bogus. So we'll see. That's ratchet. Maybe this generation. Maybe that was. What's bad again? What's bad? What's bad? What? Whack. That's whack. That's ratchet. Okay. Right now now. This is whack and this is ratchet. Okay. Of course, when I think of whacking, I think of a fly. Smacking or whacking a fly. I think of ratchet. I use that to put things together. We got to explain who these dudes are. We got to explain these who these dudes. This is a definition, and this is where we say, okay, we're delta x is the length of the domain that we're using. Delta x is the distance between B and A and the domain, and we're chopping that into n parts. We're chopping it into n parts. And now I've got to explain who these domain values are. Who these domain values are that we're actually plugging into our function. Well, x0 is A. x1, you go over one more delta x. x2 is equal to A plus 2 of those delta x's. x3 is equal to A plus 3 of those delta x's. And this keeps going until we reach xn, and the last one we need is A plus n delta x. You know, like Dr. Warren, is there a faster way of writing all that? Is there a fast way of writing all that? And the answer is yes. We just say x sub k is equal to A plus k times delta x, where k is equal to from 0 to n. So this is just a shorthand of writing all this. All of this stuff in that box is captured by that. But Dr. Warren, come on. Don't you remember Don't you remember this? Don't you remember that? That's the definition. That's what we do. We don't do this. We do this. Where capital F prime is equal to f of x. We don't do this. We do this. Guys, in the real world, in technology, where we actually have real applications, most integrals don't have functions whose derivative is equal to that. A lot do, especially in 236 and in 235, and in Calc 3. But most real applications, when you face an integral, you can't use the fundamental theorem of calculus. Even a very simple function, this guy, that guy does not have an antiderivative. You cannot find a function whose derivative is e to the minus t squared. You know, like with Dr. Warren, if it doesn't have an antiderivative, it can't be important. If it doesn't have an antiderivative, then it's not important. Well, let me graph this for you. Is that function important to mankind? Is that function important? Okay, all the standard normal distribution, area under that curve ends up being probability. That's why in all of those statistics books, when you look at the back, there's pages and pages of numbers, approximations to that area. Or now they just use software. You have to understand this. Guys, the physics is in that definition. If you want to use this as a tool, in applications, it's in the Riemann sum. If you want to use the derivative as a tool in applications, you've got to understand the limit definition. If not, you're just checking off prereqs towards a degree. It's me, Dr. Warren. I'm in. I don't want to learn. I just want to get some grade in this class. Giving up on an A. I'm just gonna But if you really want to use this as a tool like Newton did, you've got to embrace it. You've got to embrace it in its dirtiness. The units are here. The units are here. The units of the derivative are in the definition. Okay. But then this ain't Calc 1. This is an integral of a real value function. Guess what our definition of the integral of a space curve is defined in terms of? A limit. Calculus is about limits. So let's do it. I've got a space curve. I'm not going to ask you to give me a space curve. Let's just do it. Imagine that I've got a space curve. I've got a domain for my space curve. And then I want to integrate. I want to integrate that space curve. Well, math is proof. I need a definition of what this means. Well, it's defined in terms of a limit as n approaches infinity. Then it's defined in terms of a summation. It's defined in terms of a summation. Where k is going between 1 and n. Where k is going between 1 and n. And then can you guess what the next thing's going to be? Can you guess what the next thing's going to be? Can you guess what the next thing's going to be? You're going to take your space curve and you're going to evaluate it at some points t sub k in the domain. What do you think the next thing's going to be? Delta t. Now what's bogus, what's ratchet and whack? What's ratchet and whack about this so far? Who haven't we explained? Where delta delta t is, where delta t is e minus a over n. And these t sub k's are equal to, these t sub k's are equal to 0. Let's write it out pretty quickly. It would be a plus t times, sorry, a plus k times delta t, as k runs between 0 and, as k goes all the way between 0 and n. Now this one has some wonderful geometry associated with it. Most kids will remember this. You got a function, here's your y-axis, here's your x-axis, here's your a, here's your b. You're chopping this into some parts. Here's x0, here's x1, x2, x3, x4, x5. Here's my f of x1. And then if I look here, this would be like f of x1 times delta x. My delta x's are here. And lo and behold, this sum, 1 to 4 here, approximates the area under the curve. You guys remember that? You guys remember that? But guys, here, you don't even have a t-axis. You don't even have a t-axis. T is kind of like over here by itself. We're still chopping it up. And R of t is a what? R of t is a what? R of t is a what? Space curve. R of t is a space curve. So yeah, you might have an R of t0, then R of t1, R of t2, but like, what's the geometry where you don't even have a t-axis? The physics is here. The applications are here. This is the application. The applications are here. You must embrace the limit definitions. Look at somebody and say that. You think I'm lying? No, I'm not lying. I mean, guys, you've got to embrace the limit definition. I know they scare you. I know they scare you. This is the way Newton thought. Newton did literally the impossible. Newton did literally the impossible. When Newton came up with calculus, people weren't really sure. I mean, it was a nice idea of this limiting concept, but they weren't really sure. But think about 1700. How was most merchandise transported? Carriage. But how about like some big merchandise? How was that transported? Train? Yeah, that's 100 years, 150 years from now. How was most merchandise transported? How was most travel, real travel done? By ships. By ships. Okay, now imagine how many people have ever been on a ship before? It's not too far. It's not too far where you can't really tell much off of land. Does that make sense? You're not even get a mile away from shore. Get a mile away from shore. Good luck. How do they do most of their navigation? Like a compass. You're like, oh well, I mean, like map. They had a map. They used their phone, Dr. Warren. That's what they did. They used their phone. You got a map, you're out in the middle of the ocean, you're like, I-81. Where's I? Almost all navigation was done based off of stars. But the stars are changing. The Earth is moving, depending on where it was. Almost everything was based off of astronomy. Not astrology, astronomy. A comet was supposed to come across across the United Kingdom. And they lost it. They couldn't see it. I think it was a cloudy day. And Newton made a prediction with his calculus that in August on this day, at this time, at this angle, they would see the comet. And literally, like to the minute, the comet appeared. And it was that moment where they realized everything's changed. Everything's changed. Now, when we talk about motion, when I talk about motion in Calc 1, all I can really do is this. How was that for athletics? Let's try that again. Let's take out the springboard then. Okay, so all I can really do is this. All I can really talk about is motion in one dimension. Height, maybe motion this way. I can't really talk about motion like we understand motion in the world we live in. All I've got is like something like height versus time. Now, if I want to talk about the motion of something, when I want to talk about the motion of it, what's Newton's law that pretty much governs motion? F equals ma. Force is equal to mass times acceleration. Now, if I'm really ignoring almost every force, if I really think about, is there much wind resistance in this room? No. So I'm thinking about really the thing that's most working on that eraser. What is that? Gravity. Really, the only force really working on it. Well, there are other ones, but ignoring them in a simplistic model, we would say our gravity is our force on there, and so my force, is gravity changing much between the ceiling and the floor? Is gravity changing much? Now, if I threw it into outer space, might gravity change a little bit as I move away from there? So I really think this is the primary force. It's working against the eraser if I'm calling that up. Now, if this represents the displacement, height versus time, then what represents the acceleration? What represents the acceleration? Before Newton, you're screwed, right? I mean, but Newton was like, okay, well, if this is the displacement, then that would be the velocity, and this would be the acceleration. Now imagine that. I mean, let's think about this. Please, I implore you, please, Emily, Robert, Red, Rachel, please teach your children the metric system only. Please only teach the metric system. Let's be the generation that brings the U.S. into the world of the metric system. Okay, but let's imagine that we're measuring in feet per second. Okay, so we got that. So we've got feet per second. Okay. So if I'm thinking about, well, what are the units of this derivative then? What are the units of this derivative? If this is feet, if this is measuring feet at time t in seconds, then this would have units of feet per second. And this would have units of feet per second squared. Oh, but math is proof. Why? Dr. Warren, that's the derivative. It's feet per second. And the second derivative is feet per second squared. Why? You're like, well, it's easy, Dr. Warren. What's coming out of the function here is feet. What's going on is seconds. So this is going to be feet per second. What's coming out of the function here is feet per second. What's going in is second. So this is going to be feet per second squared. And then I ask, again, why? And kids are like, I don't know. Like, it's because you don't remember. units of, the numerator have units there, the numerator has units of feet, and t is measured in seconds. It's clear it's feet per second, if you remember the definition. If you're just memorizing formulas, the derivative of t to the fourth is 4t cubed, Dr. Warren. Good luck using that in any application. Now, why is h double prime? Why is h double prime? Why is h double prime of c has units of, why does that have units of feet per second squared? It's because it's defined in terms of a limit. Again, there's a t minus c, it's a derivative. But now it's h prime of t, and this is h prime of c. What are the units of this? What did we just find the units of this to be? Feet per second. What's the units of this? Feet per second, and we have do some simple grade school stuff. You get feet per second, feet per second, feet per second squared. What would the units of the 34th derivative be? What would the units of the 34th derivative? That has no physical application whatsoever yet. Be feet per second to the 34th. Okay, same application. What's the units of that? You're like, I hate you, Dr. Warren. I just hate you. I hate you. Guys, if you don't remember the definition, you're screwed. It's defined in terms of a limit. And it's right here. It's the sum of k equals 1 to n. In this case of h of t sub k. H of t sub k times h of t sub k times delta t, where delta t is equal to b minus a over n. And you got your units there, guys. If you look at this chunk of delta t is going to have units of seconds. You're taking that time domain and you're chopping it up into pieces. So this is going to have units of second. However, h of t has units of feet. So your units are feet seconds. Like, what the hell is that? That's why you never really talk about the integral of displacement. You don't really talk about it. It doesn't really have much physical dimension. It doesn't have much physical interest. We're measuring in feet seconds. Dr. Warren never have anything stupid like that. You ever heard of foot pounds? Have you ever talked about foot pounds before in physics? Newton meters? How about Newton meters? Okay, but imagine that I had velocity, which has units of feet per second. Imagine that I'm integrating velocity. In the same way, this has feet per second. If I remember the definition, this is seconds, and the integral of velocity would have units of, feet. The units of velocity would have, do you see how this can be applied to anything, guys? Sorry, I just get too excited. Okay. Back to here. I love these boards. Feel powerful. How cool, like, you forgot anything was under there. And I'm like, back to here. It's like I had it planned. Nope. Just don't look. More. The things I do to keep you awake. I know how long it is to sit in an hour and 15 minutes. I go to faculty meetings. If you think class is bad, you should go to a faculty meeting where everybody's opinion matters. I don't think it was meant for the business. I really think it was business world where people could go, no, dumb idea. Just a dumb idea. That's the dumbest idea I think I've ever heard. Why don't you not speak for the next hour, okay, please? You just can't say that. Like, oh, that's interesting. Inside you're like, that's a dumb idea. But we're faculty. We're in the academic community, the ivory tower. And then there's always the one person that always has to talk. Have you ever been in a group and that one person always has to talk? And you're like, if you so much as say another word, I think I'm just going to pour gasoline on myself and light myself on fire in protest. Just because I don't think I can hear your voice for another minute. Okay. sorry, capital over here. This is our definition of the, I don't know. The integral of a space curve or a vector valued function. What's the definition of a vector valued function? An order triple of 3 real value functions. Oh, look at how nice this is. Like this, like this. So if I think about it, we're not going to invest a lot of time in this. But if I think about this, this would be the same thing as the limit as n approaches infinity of the vector sum k equals 1 to n of 3 real value functions. X evaluated at, by the definition of a real value function, by the definition of a vector value function, I would have an x sub t sub k, a y sub t sub k, and a z sub t sub k. And all of that times delta t. Now we have 3 multiplications. We have 3 multiplications on V. What are they? 3 multiplications in our vector space. What are they? Dot product, a cross product, and a, I have nothing for scalar. So we'll do this. Dot, cross, scalar. How many people recognize that? How many people recognize that ain't a product? How many people recognize that ain't a product? That's a vector. Explain this. Explain this. Not as a sorority or a fraternity. Explain this. It means summation. What word is in summation? What does sum mean? Addition. So this represents vector addition. Do we understand how to do that? Do we understand how to do that? This is cross, dot, or scalar. Do we know how to do that? Do we know how to do that? Okay. With a little bit of dotting, I'm sorry. Oh, I just glitched. How's that? I'll be breathing that chalk in the rest of the day. I'm such an idiot. What time is class in? Look at your watch, or whatever you got. Does anybody have an iWatch? Does anybody have an iWatch? Do you like those or not? Do you like them or not? Okay, kind of, okay. I'm thinking about it. How many people think they could do a scalar multiplication? What would I do with that delta t? What would I do with that delta t? What would you do? Yeah, we call it distributed. Scalar multiply it, distributed. So what do you go there? 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 What do I do it? And what do you go there? Now, how do you add 2 vectors together? How do you add 2 vectors together? A vector plus a vector is a, geometrically, a vector plus a vector is a vector. How do you add 2 vectors together? Add their components together. So imagine that I added all these up. Then it would be the sum. It'd be the sum of all these components. And in here I would have the sum of all those components. And in here I would have the sum of all those components. Does that make sense? And all of them would be multiplied by delta t. So just using vector addition and scalar multiplication, I'm not making a proof. There's no proofs next Friday. I'm not making a proof. But by vector addition and scalar multiplication, this is the same thing as the limit as n approaches infinity of the vector of all the components added together k equals 1 to n of y sub t sub k times delta t, and the sum of k equals 1 to n of z sub t sub k times delta t. And I'll let you write it down. You'll write it down better than I've got it. And all I've done is use vector addition and scalar multiplication. Now when we have a limit, of a space curve, when we have a limit of a vector valued function, a limit of R of t, we define that to be the limit of each of the components. This extends here. This extends here. I can take this limit, and it will go to that component, and that component. And I guess I'll go up here for the lack of space and time. So this would be equal to the vector. This would be equal to the vector. And by vector, I really mean vector. A vector is a order triple of 3 real numbers, where the first real number is the limit as n approaches infinity of the sum of k equals 1 to n of x sub t sub k times delta t. I'm so freaking lazy, I'm not even doing the middle component. The last component would be the as n approaches infinity of z sub t sub k times delta t. But Emily, a vector valued function is an order triple of 3 real valued functions. So this is a Riemann sum of a real valued function. This is a Riemann sum of a real valued function, where delta t is b minus a over n, and these t sub k's are equal to a plus k times delta t. Is that not this? Is that not this? Is that not this? Here, f would be, here f would be, here f would be, here f would be the real valued function x sub t. Here f would be the real valued function y, and here this would be the real valued function z. Where does that limit go? It goes to a number. Well, at that point, I don't know. Do we have something that looks like this? Do we have something that looks like this? Is my delta t b minus a over n? Is my delta t b minus a over n? And I got to ask, are my t sub k's equal to a plus k times delta t? Is that what we have? We have all of that. What's that symbol? Just wondering. What's that symbol? What does that mean? What does that mean? Those are the same value. So where does that limit go? Well, the first component would be the integral from a to b of x sub t dt. The next component would be the from a to b of y of t dt. And the other component would be the a to b of z of t. And I go, Dr. Warren, boy, why are you dragging me through this mud? I'm hungry. Don't you get it? I didn't eat. I had to climb out of bed to get here. And guys, just saying, like, if your phone goes off and you feel physical pain in your brain, if your brain's like, oh gosh, where's snooze? Go to bed earlier. Just go to bed earlier. I mean, if you're having physical pain, okay, Dr. Warren, you don't understand. I'm way too busy. I'm way too busy. No. My daughter plays that on me. I'm way too busy. I'm way too busy. Go to bed. Go to bed. What did I just say?
Got that.
No, take one. Say that one. Why the hell did you drag me through this?
What the hell are you doing to this?
You just had to ask. You set me up, Dr. Warren. Give me a picture. Beastly. What's your last one? What's your last root value function going to be? What?
1 over t.
1 over t. Beastly. Could we have some domain issues? Just wondering, could we have some domain issues with this puppy? We definitely don't want 0. We definitely don't want 0. And we don't want any pi's over 2's. We don't want any pi's over 2's. So, you know, maybe we could go t equals like open interval pi over 4. Open interval pi over 4. Maybe we just won't go, let's not do 5 pi over 11. There we go. There's my domain. There's my domain. Now imagine I said, guys, what I want you to do is find this integral. What I wanted you to do is actually find the vector that this integral is equal to. I gotta ask you, do you want to use this? Do you want to use the definition or this theorem? Do you want to use this definition or this theorem? The theorem. Is the theorem true?
Yes.
Does the theorem follow directly from the definition? So then this would be nothing more, and I say that kind of almost as a jest. This would be nothing more than taking the integral from pi over 4 to 5 pi over 11 of secant of t. Same thing here of t dt. And the same thing here of 1 over t dt. It'd be those numbers. It'd be those numbers. Is this calc 1, calc 2, or calc 3? Is doing this integral calc 1, calc 2, or calc 3? Is doing this integral calc 1, calc 2, or calc 3? Calc 1. Can anybody think of a function? Let's use the fundamental theorem. Thank you, Newton. Can anybody think of a function whose derivative is t? Tell 1/2 t squared, so this would be 1/2 t squared. Now, I'm not doing any more than this, but putting 5 pi over 11 and pi over 4, which means plug that in and get your calculator. How about the next one?
LNT.
LNT, awesome. Was that Mason? Mason, was that you? What's your name again?
Sean.
Sean, thank you, Sean. Natural log of the absolute value of t, yeah. Between 5 pi over 11 and pi over 4. Get your calculator. How about that one, boys and girls? How about that one? What's that one? Natural log of the absolute value of secant of t plus tangent of t. Yikes. Evaluated between pi over 4 and pi over 1. Yes.
Do we have to remember how to do all those for next Friday's test? Like trigonometry, integrals, and derivatives?
Probably no more than I would put on the homework.
Okay. Would we have to know like that one or?
You definitely would have to know this.
Tangent? Yeah,
Okay, I mean, I don't know how much, I don't know, does anybody remember the integral of tangent? Anybody remember the integral of cosine? Anybody remember the integral of t to the fourth? Like, okay, I got that one down for. I have kids come in, I had calculus, so I asked them something like, what's the integral of secant? I'm like, okay, you haven't had calculus. You know 205 calculus. Sorry, ISAC calculus. I won't go there. I'm already over time. We'll pick up with this on Monday when we talk about units of a vector. Value function. Sean, will you just stop my camera there?